it. There it goes. This is the fun stuff because this is where we get to be a little creative and decide how we want to put things together. So as we look at what the textbook says we need to do for our design process, that's some general guidelines, but everything's going to depend on what kind of system you're creating, right? So you're going to have to look at the data that you need and decide how you want to put this all together. So they have some really good steps outlined. First of all, they want you to realize that our database system needs to be modeled after a real-world system. So they show a real-world system here. We have people and maybe documents and buildings and offices, and in our facility here we have classrooms and different things that have to be scheduled. We have other systems that have to be taken into consideration. So all of these things are things that could have an impact on how we design this system that we're going to create, because we have to take all of that stuff into consideration. We don't live in a bubble, and we can't design our system as though we do. So there's 6 basic steps, and this really gets it down, breaks it down to where it's a manageable thing. Sometimes a new system and creating a new database can be a little overwhelming. So it's important to break it down into really manageable steps. The first thing we're going to do is look at existing stuff. Is there already a website that we can look at? What kind of things do they need? Are there forms they have or reports that they have that would tell us what kind of data elements are necessary? We're going to identify all the data elements. We're going to look at some sort of report and just write everything down. Customer name, customer address, all those things. Step 2, we're going to subdivide each element into its smallest useful component. That means if we have a name, we're going to break it down into first name and last name. We're not going to have both of those fields in one name field. We're going to break an address down into address line 1, address 2, city, state, zip, all those different things. No combination fields or attributes. Based on that, then we're going to have this list of all of these data elements. We're going to identify their relationships and come up with our entities, our tables. What kind of entities do we have and what data belongs with what entities? After we've done that, we're going to have a general view of how we want things to be organized. We're going to go through and add primary and foreign keys. Where do we need to have ID columns added? Then we're going to look at whether our data structure is normalized. Normalization is going to help us remove redundant data and make sure we don't have any of those logical flaws that could make the database hard to work with. And then lastly, we're going to identify indexes. And indexes are like another key, a structure that lets us access our data quickly through the database. So here's an invoice. This one looks kind of ugly. Their screenshot is not super good of it, huh? This kind of thing that you would be given. But we can take this invoice and we could make a list of all of the data elements, right, that are on it, even if we can't quite read them. But if we look at this invoice, we see, first of all, we have our company name. We don't know whether that's something that could be changing or not from looking at this invoice. I'll put it down, they probably won't. We have the address of our customer, their name, this invoice number, date, what our terms are. A lot of the same things you guys have been seeing on our invoice table for our system. That's because most product-oriented companies are going to have a table set up, a database set up, rather like ours. That's kind of logical. Now, on the invoice, we have several items that have part number, quantity, description, unit price, and extension, which would be the unit price times the quantity. We have a total down here. So we can make a list of all of these different data elements that show up on this invoice. We might have other documents to look at, but we're going to start with that one. So here's their list of all of the data elements that they found. And bless you, we might decide that something is missing off of here or something that we thought is important isn't. This is our just exploration to see what's going on, what kind of things that we need to take care of Next, now that we've got all these data elements, we can decide, oh, we're going to divide things. I already said that. Names, addresses, those easy things. We never want to be the lazy programmer that puts everything all in one field. But you guys see now that there are a lot of tools available to extract those fields out. If somebody has been lazy that way, you can get to that data. So they're thinking then, we might have some possible tables here. Maybe we have a table for vendors. We know that, we're familiar with that. And maybe we have a table for invoices. We've split up all of those items, the attributes that we saw on that invoice, and assigned them to specific entities. Now, as we look at this, we can continue and that's you. We're adding some asterisks to things. Let me go to the textbook and let's see what they say about that. Our textbook has some interesting ways. Okay, we're dividing stuff up. So they identified the data elements that are included in 2 or more tables by coding an asterisk after them. So like they say, we could use any sort of notation that we like, but that's what they used. Now they mention that for a complicated design, we could even use a case tool, a computer-aided software engineering tool. And guess what? You guys actually have one. Visio is a case tool. So if we do a database diagram using Visio, we can actually generate all of the code to define our tables using Visio because it does have that case capability. So those asterisks there are just data columns or attributes that they've noticed are in more than one place. So we're getting rid of some things that aren't important, noting things that are duplicated, moving things around as we see fit. Here we've decided that we need to keep track of each of those items on our invoice as line items. And if we're going to keep track of that, we better have some sort of account number that ties us back to our vendor or something. And then we need a sequence number, like line item number 1, line item number 2, line item number 3 on that invoice. So that might be a little different than our tables are designed, but we've got to add some things to make the data elements work together in our table design. Now they say they've just crossed out the ones that they didn't need. If they added something, they put it in italics. And there's our asterisk. Now we can start, because we've got some tables pretty well lined out here. We're getting the design set up very quickly, if you notice. And since we've got tables, now we can add some relationships. We can say that vendors can have invoices, and invoices have line items. So that relationship there, the line, is showing that one vendor, like Walmart, could have multiple invoices. That's what that triangle on that side of the line is showing. For one vendor, we have a circle. For our triangle here, we could have many invoices for that one vendor. And then for one invoice, like invoice number 1, we could have many line items, 1 through 50. That makes sense when you look at that relationship line. It's showing kind of which table is almost the owning table or the managing table. Now, sometimes when we look at tables and their relationships, we see a many-to-many relationship. In this example, we're off our other example and we're looking at an employee-committee relationship. So we can have employees, they have employee IDs, and we can have committees, they have committee IDs, and employees can serve on committees. So I could have to serve on 12 committees. So those 12 committees would all show me as a member. That's a many-to-many relationship. I can serve on many committees. A committee can have many employees. We can't handle that in our database structure. It's not a logical thing. So we have to resolve that many-to-many relationship by using a linking table. The linking table is going to give us that ability to say one employee can be part of many committees, and one committee can have many employee members. So whenever we get in that situation where we're going to have a many-to-many relationship, we have to resolve that by adding a linking table. That's just a database design thing. One place that could get us, earlier on we did a database design at the very beginning where you guys were talking about recording artists and albums, and some people put in the band that a recording artist is a member of. Well, that would have to be a many-to-many relationship, right? Because an artist could be a member of many bands, and bands can have many artists as their members. So we wouldn't be able to just have a straight across relationship. So think about that. It takes a little bit of thinking, but whenever we have a many-to-many relationship, we're going to resolve that with a linking table so that we can support that relationship in the database. Sometimes we have a one-to-one relationship. This would be the case if we have like an employee and then we have another table off someplace else that just has the employee's photo. The reason that we might want to do that is because photos could be image files, they could be very large. The database administrator might want to be able to segment the physical disk space and say this employee photos table belongs over here on our storage attached network where we have a whole bunch of space for all of those photos. Where our employees, their individual rows will be kept on our high-speed network attached storage that's faster and more expensive.
I'm sorry if this is mildly off topic, but the idea that the server can have photos begs to me an interesting question. What other sorts of things could you put on there? Like, could you, for instance, put bits of C# code on there saying this row of the table represents an object that we're going to construct in the application? Right,
why couldn't you? Because you could put, based on those data types that you guys saw last time, some of your large data types, that's what your large data types are for, is for blobs of information. So depending on how you wanted to do it, something like C# code could just be a text field.
And then it would just be a matter of getting the application to say, this is a bit of code, not a string.
Right, and know what to do with it. And yeah, you can set up images in all those large data types and different things like that that you want to keep track of.
Does it actually hold the image, or are you just holding the image location?
It's holding the image. And of course, you could hold the image location if that's what you wanted to do. You wanted to point someplace else. But yeah, it would actually hold the actual image so that you've got everything there related to that employee in the database. The one I think of, just think about like catalogs. A lot of times, if people are selling things online, they spend hours and hours taking pictures to put on web pages. And it would be a lot easier to put those pictures in a database and keep them. Okay, so we've looked at how we go through and we analyze what data elements we're going to need to keep track of from the output or the current systems that we have. We made a list. We organized it all into what tables each of those things belong in. Now, before we can get to this step, we need to do a couple of other things. We've got all these table lists. We need to add our primary keys, right? We need to go through and say, oh, vendor's going to have a vendor ID. Whatever else we have, our invoice. Do we want that to be an invoice number that we generate, or do we want it to be an invoice ID that the system generates? But we've got to get all of those keys. Now, once we've got keys, we can form the relationships in our table that we were talking about. When we have relationships, we have to decide how this relationship is going to work. So right here, if I delete a line item Does that affect an invoice for the vendor?
Should affect the invoice, but
Would it?
it's a part of the.
It's a part of it. So we might have to update our invoice total because we deleted that line item. We would have to do that in our code, right? So we would have to make sure that we had something that handled that. Because if we just let people carry, delete line item rows, we could get a messed up invoice total. What about deleting an invoice, a whole invoice? Does that affect any line items?
Yeah.
Yeah. It doesn't really affect our vendor though, does it? We could have something missing, but I mean, it doesn't affect our vendor. And then if we deleted a vendor, does that impact invoices and line items? It does. Now, if we allowed a vendor row to be deleted and we had invoices for that vendor, those invoices would now be orphans, right? They'd be out there in the database, but they wouldn't have a vendor associated with them, so they would be orphans.
Most of us who were in your class yesterday saw when you were kind of walking people who weren't taking this class through how to make a table. And one of the things you had to set was the cascade bid. Is that why that's there?
Yep. So what we can do, Seth is talking about, is we can, when we form this relationship in our database, we can say how we want it handled. Do I want updates to this vendor to cascade down? So if I update this vendor ID, should it automatically update all of the invoices? Probably. We wouldn't let that happen. But if we did, we would want that to update. And then on delete, we can also set things to cascade so that if we delete the vendor, it deletes all their invoices and all their line items, and we don't have any orphans left over in the database. So those are options that are available to us when we create those relationships. We're going to say how things work. So all of those have to do with referential integrity. How is my table referring to another table, and making sure that those keys are all in place and nothing is orphaned and nothing's invalid out there. Now, whenever we're inserting a row, like a new line item, we need to make sure that there is an existing invoice and an existing vendor. The database will do that automatically for us if we have that relationship set up. So we would have to take care of all of this stuff manually in our code if the database wasn't taking care of it for us. So all of the referential integrity that gets enforced by those relationships between our tables is really important to our system. It's going to keep everything in place. Okay, so some things here. Terms. An entity. What is an entity if you were looking at C# or some other programming?
Object or a class.
Exactly, or some other programming language. It could be a class. And then an attribute or attribute, depending on which side of the country you were born. That would be a column or a field, right? So kind of like a property. We use those interchangeably. Whenever they're talking about an instance in database terms, they're talking about one row in a table, one vendor, just like we would talk about an instance of a class or object in our programming language when we create an instance. Now, our entity relationship is that diagram we were looking at. Referential integrity is that relationship that exists between tables, making sure that our primary key, foreign key models are respected. And we declare that referential integrity when we create our tables so that the database knows about it. And we'll see that in our next chapter. Now, the foreign key constraint has to do with the referential integrity to make sure that our foreign key is valid. We know that orphaned is something that's hanging out there. And a trigger is something that keys something else to run or do something. And we can have triggers in our database that's code that's defined to run at certain points, like when a customer is inserted, so that we could insert that address table row. Okay, so our last step is normalizing. We're almost done here creating this database. And normalizing has many, many steps. Normalization is this process we go through to manipulate our data to make sure that it's all valid and that it's in the most effective manner stored so that we don't have any redundancy, we don't have any duplicate data, things that would cause us poor logic. So we could actually have like 10 normal forms, but we could go up to 3 normal forms when we're trying to normalize a database. So the first normal form, do you have your OneNote open? Let's create a notes for this chapter. Because our book kind of drops the ball on this and says, oh, you will normalize, and that's about all they say. So first normal form. If you Google this, you'll see a really long description, something to the effect of each attribute contains indivisible values, and the value of each attribute contains only a single value. Okay, so anytime you look at normalization, you'll see some great descriptions like that. What does that mean? Reduce data attributes to their lowest level. First name, last name, instead of name. All the different address fields. So that's our first normal form. That says that we don't have any data that is in a group in a higher level than its lowest level. Now for second normal form, I apologize, I did not write down the long, never-ending description. But in second normal form, we're going to make sure that no data is dependent upon another entity. So in our first normal form, after we've done this reducing our data elements to their lowest level, we want to eliminate repeating groups. I'm going to add a little bit more there. So if I had a website where people were registering and I asked them for 3 contacts from their company, contact 1, contact 2, contact 3, I would not carry contact 1, contact 2, and contact 3 on my table because that is a repeating group. Instead, I would create another table that is contacts so that they could all be held there. Now, in addition, we're going to give each entity a separate table and assign the attributes that belong to that table. And then we're going to assign primary and foreign keys. So I had that kind of all as the first level of normalization. A little bit of that and a little bit of other things. So after we've done this and we've got all our data, what we want to do here is we want to get some other eyes on this. And we want other people to look at this and say, is all the data in the right table? That's basically what second normal form is. Is it in the right table? You wouldn't believe how easy it is to end up with something in the wrong table because it's communicating, it just got in the wrong place. So it's good to have other people look and make sure that, you know, this vendor name really belongs on the vendor table. Now in third normal form, we're doing the same thing, only we're making sure that no data is dependent upon any other data in the table. And this one has some really interesting multiple sentence description if you look online about attributes and indivisible values and things like that. But basically what we're saying is make sure every one of these data elements stand on their own. If they are dependent on some other piece of data in this table, then they probably need to be pulled out into their own table. And this one is kind of vague. It just means that every single element or attribute on that table can stand alone. The name can stand alone. The address can stand alone. All right, so we're going to take all of our definition and apply first normal form, which we've been doing as we've been going through it. We're going to review for second normal form to make sure that nothing is dependent upon a different table. And then we're going to make sure that no data is dependent upon any other data in our table. It and the key are going to stand alone. Does that make sense? We want to make sure that everything's cleaned up. Here's some good examples. Here we have item descriptions for this invoice. Item description 1, item description 2, item description 3. So that's bad. Those should be pulled out into their own table, but not like this. Right down here, we have them in their own table, but notice they don't have any sort of line item number to separate them from each other. So they are redundant. They're all the same. So we'd fix all of those problems. So here is our third normal form. We have our entities set up and our relationships. Everything looks good. I don't think there's anything else. Oh, when to create an index. So an index is basically an array held in memory of a specific foreign key. So if I have a database that has 5 million rows and it's about customers, and I often want to find customers by name, then I want an index set up on the customer name. And when I declare that index, the database is going to automatically create an array, basically in memory, of all of the different names for the different customers in order with information about how to find that individual customer row. So that when I go through and query by name, I can access them all very quickly through the index. So we want to create indexes on columns that we use often in searches or joins. So if we look at our database out there, we'll see that we have a lot of indexes created on these foreign keys that we use in our joins. When the column contains a large number of distinct values that we might use to find a given record, or when the column is updated very seldom, we could use it for an index. So if we have a column that's updated all the time, indexing on that column can cause some performance problems, but it still might be necessary. So you can see that. Now we can also make an index clustered, which says we would like to keep the actual data rows near this index value on the disk. So if I set up an index that was by last name and I clustered it, when I got to my Smiths, my last name for Smith, all of my data rows would be saved on disk with that index structure in the same place. So as I read through my disk, I would be getting all of my data in last name sequence because that was a clustered index. So we want to make an index clustered when it's the primary column that's used in almost every search condition. We want the column to be small, values to hardly ever change, like someone's name or a company name. We can really affect the performance of our database. A composite index is one that's created on multiple attributes, maybe like last name and first name, and we can create an index like that also. Sometimes when you look at normal forms, it will be noted like this: 1NF for first normal form, 2NF for second normal form, and 3NF for third normal form. Okay,